Hello, we are group 18, and this is my group member, and me, Jing. So this project is about turning sunlight into usable power, so let's begin.
Hello everyone, I'm Shuanghe. Our team's final project is a portable solar charging system that can efficiently convert solar energy into a stable DC output under varying sunlight conditions, powering small electronic devices. In the age of AI, this system can not only provide reliable off-grid power for AI devices, but also upload real-time voltage, current, and temperature data to the cloud for AI to analyze and optimize. Structurally, the hardware includes a solar panel, a boost converter module, sensors, and a control unit. The software uses Arduino to control PWM and collect data, with LabVIEW for real-time monitoring and cloud uploading.
Hello everyone, this is Trudy from Team 18, and you can see this diagram is about our LTspice simulation system. We can use it to find the best frequency. And so you can see this diagram, we find when the frequency is between 30 kHz and 40 kHz, the efficiency is the maximum. It is about 90%. And for our project, we use the frequency is 31.25 kHz, and we get the efficiency is 87%. So maybe some influence were not considered. We need to think more for the next time. So second, we can simulate that. For our simulation, we find that when the duty cycle is 0.482, we get the maximum output power, but actually the duty cycle is 0.45. So this is similar to our simulation results. So we can use LTspice to predict the duty cycle and maximum output power in advance.
In the schematic, we divided the system into several key modules. First, the boost converter. It consists of an inductor, MOSFET, and diode, and is used to step up the photovoltaic input voltage to stable output. We added capacitors and resistors for filtering and voltage stability. Next, the current sensor. This IC allows us to measure the PV current in real time, and the data is sent to Arduino for power calculation. Then, the temperature sensor, which monitors the PV module's temperatures under different conditions to ensure safe operation. We also include an indicator module. An LED shows the operating status of the system in a simple and intuitive way. On the PCB layout, we optimize the routing. The power traces are made thicker to reduce resistance, while the signal traces are separated to minimize noise. The components are compactly placed, which shortens the connections and improves both efficiency and reliability. Overall, this PCB integrates the boost converter, sensors, Arduino interface, and indicators into one board. This makes the system easier to test, more portable, and more stable.
This is our front panel of LabVIEW. This for real-time data is read from Arduino, and the data here are calculated from here. And there we can set up our PMW channel, delay time, AI channel, and duty cycle. Also, there has irradiance we can set up. This is our block diagram, and here is the cloud uploading system. We will upload every 50 seconds. Here we can calculate the installation. This part use a formula to convert the voltage to the temperature in degree, and we can use the voltage divider to find the V out and apply to the Ohm's law to calculate I out. V in is obtained directly, while the V in is calculated using a current sensor. And here we can get the output power.
Here we designed a PCB board, which integrates key components like the current sensor and boost converter. This board is hardware foundation of our system. The PCB is connected to an Arduino board and a solar panel, allowing us to test the real input and output behavior under actual conditions. This setup helps us observe how hardware responds to changing sunlight. The PCB connected to the computer through Arduino, with LabVIEW running on the screen. Here we can adjust parameters, monitor data, and fine-tune system in real time. This step demonstrates the integration of hardware and software, ensuring the predicted design matches the actual performance. For testing, we use different methods. First, we tested outdoors under real sunlight. This helps us to see how the system performs in actual environmental conditions with natural changes in solar intensity. Second, we tested indoors under a strong lamp. This gave us a controlled and stable light source, which made it easier to repeat measurements and fine-tune our parameters. Together, these two methods give us both realistic performance data and reliable, repeatable results.